Okay, so let's work on this problem. Two beams pinned together. Here, contact, mu s, coefficient of friction. We need a better pen. Alright. Then we have mass here. Say this is theta. And we want to find reaction at this point A. Increase the intent. Okay. Want to reaction at point A right here. Mass M. Theta. Symmetric. Length L. And assuming that this starts to move, we want to find internal reaction at point A, internal loading at point A. In particular, internal bending moment at point A. This is the question when it's about to move. Well, the first thing I do, choose a system. So let's go through these 5 steps. I would consider this one system, call it sys1. Consider this one, sys2. Now go to next step, draw FVD. If you draw FVD, you're going to have, let's put some labels on the point. Let's say this is B, C, D. Therefore, that's going to be normal force at B and the friction force at B. Remember, the friction force should be opposite to the possible direction of movement. And because from the intuition we know that this load mg is going to cause these beams to open up, therefore the friction force should be the opposite direction of possible motion. So that's the reason I put it to the right. FV and B, there is no bending moment because it's a contact point. Then you continue, go to D, dx, dy, and when you come back to the start point, then you're done with surface force, no body force. As I said, just ignore the weight of beams, but not friction. So this is pretty much FVD for system 1. Now you go to FVD for system 2. And draw system 2. So don't forget, this is going to be theta. And when you want to do it for system 2, all you do, you put the opposite, dx goes this way and dy goes this way. Then you have a mg that acts right here, but you can move it across the line of action, which is this dash line. So I just put it right here, move it up, mg, and then you're gonna get 2 reactions, one friction, F at C, and at point C, no bending moment. That's it. So basically you can say, well, I got 2 systems, each system has 3 equations, so I have 6 equations, and on the other hand I have 6 unknowns. And what are my unknowns? dx, dy, fb and b, FC and C. So 6 unknown, 6 equations, then you can solve it for arbitrary m. But look, when I say we increase this mass m, that means that we put some, if you consider this as like a bucket, right? So you have a bucket like that, and you put little small masses in it, like each one dm, increase putting mass in it such that this entire structure is about to move. Okay, so in that particular moment you have a particular mass, which is some of these little dm's in the bucket. That particular mass, we have this structure start moving, so it's like onset of movement, right? In that particular case, we have this additional equation that must be satisfied. Additional equations are F at B becomes mu s normal force at B. In that particular moment, the friction force at B satisfies this additional equation. And also, N as at C is going to satisfy, F at C, friction force at C is going to satisfy mu s times NC. So having said that, we go ahead and write the equation. I know that my purpose right now is to find all these equations, all these unknowns. So because if I find that, then I can just simply cut it here, right, and consider the portion of system on the left, and then I can draw FVD. So let's say I've already find my FB and NB, right? Then I can just consider this system. So here at point A, you have normal force at point A, the shear load at A, and that's the thing that we're trying to find, the bending moment at point A. That's the objective of the problem. Once you get these two, right, then you can just write one moment equation about this point, and then you can get MA, and you're done with the problem, right? So before I do that, I need to find external reactions, which are the 6 unknowns right here. So what I would do, first I would find dx and dy, and then using the information for dx and dy, then I go ahead and write equation in each one of system 1 and 2 to find either NC, FC, or NB and FB, right? So in that case, if I find dx, dy, then I can just simply consider this system on the left, system 1, and get FB and B. Once I have FB and NB, then I have this part, then I can immediately get MA. So that's the plot. Before you start solving the problem, you have to have some sort of planning. So let's write moment equation. I know that I can generate six equations, but I want to save the time. So the first equation I write is, the first equation I write is summation of, where is it? There you go. All right, summation of moment equation about point B in system 1. This is system 1. This guy on the right is sys2, right? So in system 1, summation of moment about B must be 0, because this is still in equilibrium, although it's about to move, right, because of increasing the payload mass m, but it's still in equilibrium, so this equation is valid. Now you just expand that, so nothing comes from FB, nothing comes from NB, then you have dy, move this dy down, so the moment come from dy is dy times the moment arm, which is L sine theta positive, and then negative dx times L cosine theta 0. This is one equation that confirms summation of moment about this point B at system 1. Then you can go to system 2 directly, say summation of moment about point C in system 2. C in system 2 must be 0. I'm just trying to get two equations to relate these two discrete parts of the structure together, because the only way they communicate is through dx dy. Okay, so if you write that, then you get mg times, look, you need to move this mg down, so this is going to be your moment arm. So the moment arm, if that's theta, then this is also theta. So the moment arm is L over 2 sine theta times mg, and it's positive. Then you go plus dx times L cosine theta plus dy times L sine theta. Dx L cosine theta, dy L sine theta is equal to 0. So these two little things, they simply give you two equations for two unknown dx dy. And now I have my plan. Once I get dx dy, then I immediately go to system 1, the green system, the cut system, you see? Let's show it again. Let's call this system 3. This green system right here, system 3, which is cut through A from the left. Then I can write a moment equation about point B, and then I can get the, I know that here at A, I have three components, MA, NA, VA. Then I can just write moment equation about A, summation of moment about A, and get bending moment at A, right? So let's do that. Again, I don't need the keyboard, let's put it back here on the left. So let's solve these two equations. If I solve that two equation, then I get first equation, let's solve, this is 1, 2. If I solve 1, then I get dy L sine theta is equal to dx L cosine theta. Get rid of L, so dx becomes dy times tangent theta. So dx is equal to dy times tangent theta. So if I give you theta, something like theta is equal to, for example, 25 degree, then you substitute there and you get dx is equal to a decimal number times dy, right? So, but this thing looks a little bit more complicated, because why? Because it's parametric. You don't have numbers here. But the procedure is exactly the same. So let me find my keyboard. Where did I put my keyboard? There you go. I need to erase this last part to open up some space. So that's the solution of the first equation. Then I put it in the second equation. Then I put it in equation 2. If you substitute equation 2 for dx, then you get, take that to the right, then you get, instead of dx, you put dy tangent theta, then you multiply by L cosine theta, so this is this term, plus dy L sine theta is equal to, take mg L over 2 sine theta to the right, so you get negative mg L over 2 sine theta to the right. So here, divide by L and factor it, right? So if you divide, let me grab another color here. You see, if you divide both sides by L, you're going to get rid of this L here, here, and here, right? And also factor out dy. So what do you get? You get, need black, there you go. Then you get dy times, so tangent is sine theta over cosine theta, and this cosine cancel out with this, so you get dy times sine theta, and there is no L, is already cancelled, plus there is another one, sine theta here, is equal to negative mg times L, sorry, there is no L, L is already, sometime we need to erase it, okay, mg times half, negative mg times half times sine theta. So do the algebra, go ahead and you just say 2 sine theta times dy is equal to negative half mg sine theta. We get rid of sine theta, and then we get a simple equation for dy. dy is equal to negative 1/4 of mg. Usually because of symmetry, you see the structure is symmetrical. You cancel out some you get some data that are theta independent. So if you get rid of sine theta here, you divide both sides by 2, so you get dy is negative 1/4 mg. And then you can put it either in equation 1, this one that I'm highlighting, or equation 2 to solve for dx. So if I have dy, let's put there in one of these equations, let's put dy is equal to, let me do it here, dy, let's use for example equation number 1, right? Then you have, instead of dy, put negative 1/4 mg times sine theta is equal to dx times cosine theta. Then you solve for dx, you get dx is equal to negative 1/4 mg times tangent theta. So all I did was substitute dy in equation 1, this equation on top, and then you get negative 1/4 mg for dy times sine theta, because there is no L, L cancel out both sides in equation 1. Then take dx cosine theta to the right. Then you solve for dx. So you simply get negative 1/4 mg tangent theta for dx. Now I have my dx and dy. Now I go back to the problem here. Now if I if I write equation in this system, summation of force in x0, summation of force in y0. In fact, in that system, I need to draw it here one more time. You have this part of beam, dx was this way, dy was originally taken that way. Please note the sign must be preserved here, dx, dy, and then fb and b. fb here, nb here, right? So, and your point that I'm trying to find is located A. This is the point that I want to find MA, the bending moment at A. And the problem is pretty much done after I do that. So before I do that, I say in this system, system 1, summation of, I haven't cut it yet. I'm still doing external analysis and external reaction analysis. So I say summation of forces, x direction should be 0. That would give me dx plus fb is equal to 0. Summation of forces in y should be 0. That would give me dy plus nb must be 0. Now solve for fb and mb. Okay, solve for that. What do I get? Take it to the right. fb becomes negative dx which is equal to negative of negative, which is positive 1 force mg tangent theta, and solve this equation. Now you get mb is equal to negative dy. So dy was negative 1 force mg, so mb is equal to negative dy, which is negative negative, which is positive 1 force mg. You see? So basically, if I go ahead and do my final internal cut and take this left part of the system, I could take the right part of system, and I didn't really have to solve for FB and MB in that case. But they should all end up to the same conclusion as long as the problem is well defined. Sometimes we face with what they call it inconsistency or not well defined problem. But if the problem is well defined, it doesn't matter what part you take, you should end up with all same answers. So I take the one on the left, and if I do that, I'm going to draw the final cut system. So this is cut at point A with a little bit of exaggeration, and this is point B. Then I need another color for forces. FB, its value is equal to mg over 4 tangent theta, mg over 4 tangent theta, and is given in direction shown here. And NB, its value is mg over 4. So this is basically the value for MB, mg over 4. And then at A, I'm going to have a bending moment, which is this way, MA. I'm going to have a shear, because its left system is downward positive, V at A, and normal force at A, which is this way, NA. Now look, my objective right now is to just find MA. Right? I didn't ask for VA or NA. So you just go ahead and say summation of moment about point A in system 3. Let's call this green system on the left system 3, and the green system on the right, which we're not going to use it, but just let's call it system 4. That equation, summation of moment about A in system 3 must be 0. Now let's expand that. You get MA positive, and you don't get anything from VA, you don't get anything from NA, and then you get a positive contribution from this one, the friction force, which is mg, its values, mg over 4 tangent theta, the value of force times moment arm. We look here, that angle is theta, right? So the moment arm is going to be L over 2 cosine theta, and this is positive. So positive mg over 2 tangent theta, this value of force, times moment arm L over 2 cosine theta, and it's positive. Now also we have a contribution from this guy, which is equal to negative mg over 2. So the value of force is simply mg over 2. There is no angle. Negative mg over 2, over 4, negative mg over 4 times L over 2 cosine, sine theta. Sine theta is here, from here to here. This is moment arm. L over 2 sine theta. So L over 2 sine theta times mg over 4, and it's negative. This summation must end up to 0 according to laws of equilibrium. So mg over that's an interesting part. It looks to be a complicated relation, but look, we can simplify that. This tangent becomes sine theta over cosine theta, and because this is at bottom, we cancel out with this. So again, you get MA plus mg over 4 sine theta L over 2 negative mg over 4 L over 2 sine theta is equal to 0. So they will cancel out and you get MA is equal to 0. So when you actually cancel out the bottom of this tangent with cosine, then both terms become sine, because one of them is positive, mg over 4 sine theta times L over 2, right? And one of them is negative, negative mg over 4 L over 2 sine theta. Then they identically cancel out. So the moment at point A becomes 0. The internal moment at point A becomes 0. So this is the answer to the question. The internal moment at point A is 0. And I mean, you could just say moment is 0, but nobody could guess that. It's not intuitive. You have to go through the equation to get this result. But I'm going to check your answers and see who got this answer to grant a final waiver.